We just got the broadcast started now, and we just have enough time that the gardeners are outside right now with their blowers. So if you hear some background noise, that will be the gardeners taking care of the landscape. Just got the broadcast started now, and we just have enough time that the gardeners are outside right now with their blowers. So if you hear some
There's a lot of
background noise, that will be the gardeners taking care of the landscape. Just got the broadcast started now, and we just have enough time that the gardeners are outside right now with their.
Hello, Joe.
Hello.
Yeah, again, there's a lot of.
How are you doing now? Can you just one now?
Yeah, I'm fine and doing fine. And I don't know, for some reason it went into echo, the previous dialogue.
It's okay. Looks like we're down to one line now. Some of that seems like there was something else open, but I think we're okay now.
Okay, fine. Go ahead.
All right. So let's see. Now, for the structure and model activities, our current activities is what we'll be talking about. And our current activities are all focused on one specific aspect. And from Kevin's presentation, which was just excellent, bringing all these different trains of thought and all these different ideas together and showed how they mixed and to get us to where we are today. The bottom line up front of what I want to emphasize is Boolean reasoning. Out of the people that actually have implemented different types of structural modeling systems, Warfield was the only one that I could find who not only designed analog computers, but he also designed digital computers and used Harari's work in binary matrices to introduce Boolean reasoning into his work. So that's going to be a theme that we'll be talking about all the way through here. And I will try to emphasize that in the different people who had various and related techniques as we go through. So, all right. So just an overview, a little bit of what I'm going to talk about. Some fundamental areas, which are systems science, engineering and thinking, complexity reduction techniques. Most everyone that's involved in this field uses these approaches to reduce complexity or the complexity of the system that they have or that they're faced with at their time and their context. Then we'll look at the mathematics of structure and talk about the value that this approach brings. And then we'll also talk about current complexity reduction techniques and activities, some of our software that we've put out on the web, some of our open source activities, and how we believe we can add value by making things very clear with open source software and bringing the language, the logic, and the mathematical software components together in a very clear way. So we've been doing this for a while, and one of the things I'd like to point out is the fact that we have a lot of resources on the web. So I'm just going to show 3 specific components of this list, but there's a long list here. And there's a link to our website. The website has a lot of publications. It has our structural modeling project. It has right here, the history material that Kevin just did will be posted there. The structural modeling project, my presentation will be posted here. Of course, we have a YouTube site, and so the material on YouTube and these recordings will be there. We have our technical reports and our publications are listed in this particular area. So the website's a good resource if you are interested in finding out about more details of what we've been doing and looking at the software and the detailed technical approaches. Then here's a GitHub repository for the INCOSE 2015 symposium tutorial that we did. And in that particular symposium, we brought together a lot of this information. The slides and the material from the tutorial are there. But a key aspect about this repository is it links to all the other repositories and papers and information that we have available. So if you download this presentation, this will be a key switch or a key switchboard into the our work and what we're doing with it. Then, of course, we have basic structural modeling repository with software. We also have our papers on ResearchGate and our course, our Google group, and then the YouTube channel where this specific, where these videos will be posted. And right now, of course, you can see this is a live session now. It's here on YouTube. And if you go this way, if you go back on the videos here, you can see that I have videos that actually go through the fundamental basic structural modeling, explain the algorithm, explain the math in detail. So all those are there and available. So that's some of the available resources to people that are interested. And of course, you can always ask questions on the email list or email us directly. Okay, so what we have is we have the systems engineering main activity started about 1955 in its current form of application. And we have some of the major players are Goody and McCall, who basically wrote one of the first systems engineering textbooks. Warfield was active in digital and analog design computers at that time. Sage was an analog type of electrical circuits. Forrester at that time and actually worked in designing an analog computer that was like a flight simulator. But what he determined that basically that the analog computer, the way they were designing them, would spend most all its cycles managing itself, and there would really be very little leftover capacity to do any useful work. So Forrester then moved over to business management, took these type of techniques, feedback loops, and analog design, started applying them, and of course that's where you have systems thinking and the systems dynamic structural analysis type approach. And then George Friedman essentially worked with von Neumann during that period of time, and then worked all the way through and a career and finished up at Northrop as their one of their lead technical executives. But his work within multidimensional mathematical model management essentially says, hey, you know, we need to not simplify. We need to understand the mathematics that generates this complexity, and we need to learn how to engage it. So these people each approached the problem differently. They had different contexts, they had different objectives, but they were all focused on complexity reduction. And this has been a central organizing theme in most all the systems engineering literature that I have found. So the work that Mary and I have been doing for complexity reduction, we've come up with a couple of rules and a kind of a fundamental approach to engaging complexity. And this is a short list of the major factors and elements that are important. So to reduce complexity, the first thing you need to do is reduce uncertainty. If you have a lot of uncertainty within a structured area, then there's a lot of complexity because you really don't have the information to understand the structure. So you reduce, and you need to focus on a single system aspect or organizing system relationship at a time. So once you're doing some type of analysis, you focus on one technique that has minimum amount of uncertainty, hopefully no uncertainty, and then those techniques or aspects you can integrate using other techniques. And we use two types of languages. As Kevin pointed out, the natural language and the mathematics, there's been a historical theme of integrating language and mathematics, but that hasn't been very popular recently. So what we're doing is we're actually developing procedures and processes that map natural language relationships to mathematical relations. And it takes a natural language or an informal language and makes it formal. And it employs two structured interfaces, the natural language to mathematics interface and the mathematics to systems description interface. So we have just a pictorial of what's going on here. This is kind of the Hilbert meta-language, object language type of approach that was expanded by Warfield to apply to systems science and systems engineering. So you use the natural language, you use that to describe the mathematics or the object language. And the mathematics then, or the formal language, is used to describe the system. And I'm sure we all have experience where we basically just use natural language and use that to describe the system, which generates a tremendous amount of uncertainty and conflict about the meaning and the semantics of what the system really is and what it needs to do. So we believe that a key factor in the reduction of uncertainty and complexity is to actually use mathematics or formal object language to describe the system and not use an informal language to do that. And so given this situation, we believe that complexity reduction actually shaped the systems approach. And so, as we've talked about, the first systems engineering textbook, its whole focus was on complexity reduction of systems development and deployment and operation. As Kevin highlighted, the uniform program planning, which is kind of a precursor to the many of the types of system architecture, types of decision making, and types of house of quality and conceptual design. This large-scale planning, the unified program planning, was fundamentally drives our ability to create layered systems in a logical fashion and to thread through those logical conceptual designs. And of course, with systems thinking and systems dynamics type of complexity engagement, it helps you build a structure, but it's very has a tremendous amount of feedback and is difficult to actually find threads of logic through those. And we believe that having the correct techniques and gathering and organizing the information to apply those techniques is a key approach. And as Friedman said, you must not simplify, have to learn to fully engage the complexity of each situation. So that's kind of where we're going with the structural modeling project, is to help us fully engage all aspects of complexity in our systems. And when we're doing this, we're thinking about this activity and how we're going to do it. I always like to look at the difference between science. We talk about systems science and systems engineering, or systems methodology. We really need to compare the context and the motivations, the goals, the types of truth between these two. And I think there's some very important things on this particular chart. And the first one, of course, is that the science is the Okay, so here we go. The science basically is at a point where we need to I need to take just another little break here and address this other issue. Okay, here we go. All right. So in this particular part, we're looking at the motivation, the difference between scientific method and systems methodology. The motivation for science is usually personal need. People are just doing what they're interested in. Systems methodology is societal need, and it's kind of a goal-oriented activity. The types of truth that we're looking at here, within scientific method, we have formal truths and factual truths. But in the systems methodology, we not only have formal and factual, but we also have value truths. And what we'll be looking at in our techniques is where we integrate the formal truth, which is logical inference of all kinds, and factual truth, which is empirical knowledge, empirical information. Then you need to develop the value truth. And so when we talk about our logic and our empirical work in these matrices, then those are actually embedded in a process, like Kevin showed, the social systems, which help develop the value truth. So each different group is going to have a different set of values, and you need to actually interpret what you do in the context of those values. The logical structure is also very important. Within the scientific method, it's a relatively simple logical structure. You're going to do your experimental design. You're going to be focused on addressing your one hypothesis, and you're going to design your whole research program so that you can analyze the results from your research program and determine whether or not your hypothesis basically was falsified. But on the systems methodology side, the logical structure is multi-level, and the stress is on synthesis. In Kevin's presentation, one of the things he highlighted was the fact that even though you do an analysis, each one of these groups, on a specific aspect of your problem, that you may do numbers of different procedures and these procedures essentially would be one aspect at a time. So it's, again, the planning is different, the focus is different between the scientific methodology and the application. And these things we need to keep in mind when we're designing our techniques for engagement. And of course, the behavior is, science is not behaviorally limited. You know, individual collected people go and they pursue what they're interested in, scientific activity, they want to learn and figure out things and discover things. And scientific methodology is behaviorally limited. And it's a group activity that's constrained by budgets, goals, activities, and context. And so, again, we need to have techniques that can also be responsive to these types of behavioral constraints. All right, so once we're looking at systems and analyzing systems, we really need to talk about the kinds of systems where this applies the most. And this is adapted from Weinberg, Introduction to General Systems Thinking. But we essentially have three general groupings of system types. And as we can see here on the x-axis, starting from the origin, going to the right, the systems become more complex. And then starting at the origin and going up the y-axis, the systems become more random or disorganized. You can also think of this as just entropy or disorganization. So near the origin, we have organized simplicity. We really don't need to use complex systems techniques because we have systems that are organized. You can analyze them. They are simple machines. And then as we go up the y-axis, till we hit some barrier here where we're right here saying, oh, this is kind of like, you can think of this as we've hit the law of large numbers. We have enough events, we have enough uncertainty, we have enough randomness that we can now apply the law of large numbers in our statistical analysis. Between these two, we actually have the area where we apply complex systems analysis the most, which is organized complexity, which is too complex for the mechanical analysis and too organized for statistics. And when it's too organized for statistics, the techniques in the interpretive structural modeling, what we do, and the purpose of this, is to actually determine this organization. When we are in this area, this yellow area, where it's, too organized for statistics, when we first get there, we really don't know how the problem is organized. And so these techniques, ISM, relational mapping, that we use, they essentially are a mechanism by which we discover this organization. Once we discover this organization, then we can apply logic rules, language structure, and operational rules specifically to help us understand what's going on in a better way. All right, so now, after I've talked a little bit about what we're doing and setting the context, I'm going to change now and talk specifically about the mathematics of structure. And this is a monograph, a Patel monograph that was written by Warfield in 1974. And this specific monograph addressed only matrix mathematics. There are other forms of mathematics you can use, the mathematics of structure, but only matrix forms were addressed in this one. And that has a strong connection to Boolean reasoning. Warfield's background was in digital and analog computer design. He understood circuit theory, he understood Boolean reasoning, and he also understood the types of techniques that computer design professionals need to know. And Boolean reasoning today is mostly only worked with by people that design CPUs and silicon circuits. So we've taken all the analog design reasoning, and it's all now down into our silicon chip manufacturing. So Boolean reasoning is important, but it's a very narrowly, highly focused, highly stovepipe subject in today's application because not very many people understand it because it's all in the chip development area. So another thing that we came across, I did anyway in the research, was it's difficult to program with modern data types. If you think about when these people were doing this work in the 50s and 60s, we didn't have modern compilers. We didn't have modern data types. We didn't have integers. We didn't have Booleans. We didn't have strings. These people were systems to do what they wanted them to do basically at assembly language level. What's some of the functions that are necessary to be done within the Boolean reasoning and within the ISM techniques and the structural modeling techniques are difficult to do with modern data types. And so we've developed some effective approaches and some methods how we can use modern data types to get the types of responses we need mathematically. The subject of that study basically is the basic structural modeling, the code and the mathematics and the tools and everything that we use to do it, and the reports that talk about it are all on GitHub or on ResearchGate. So that's all that work has been done and it's been published. And if there's any questions, of course, be sure to let us know. So we're working now on some effective methods that basically we want to put into new computer code. This new computer code, we're packaging these as little web applications and putting them on the web with JavaScript. And the goal is to demonstrate a specific relationship mapped to a simple problem. And this way we'll start building a language of abstract relation types that show the natural language form, the graphical representation form, and also the mathematical form. So we were starting to do these one at a time. And when we were looking at the structural modeling and the mathematics of structure, one of the things that Warfield pointed out, he defined basic structural modeling. Basic structural modeling essentially is mathematics. It's abstract. It's abstract concepts that have no empirical information at all. And it's the area of mathematicians and it's sophisticated mathematical logic over in this area. And then there's interpretive structural modeling. And interpretive structural modeling has only empirical or substantive knowledge. These are the people that are embedded in your day-to-day complex situations and really are, have the interface to the problem that needs to be solved. And Warfield just said you needed to place these in proper correspondence. But as we started looking at how do you place these in proper correspondence and what are the mechanisms to do that, we've decided that we actually needed to have an area on this interface that we call structural integration modeling, which is the area of the systems scientist or systems engineer that actually develops the techniques, documents, and presents the techniques that actually place this that place these specific mathematical systems in the proper correspondence with the day-to-day complex problems. So we have basic structural modeling, interpretive structural modeling developed by Warfield, and Mary and I developed the structural integration modeling to actually start documenting and developing how you do this. One of the things that, besides the barrier presented by modern data types in the mathematics and that kind of have been a barrier for people actually implementing these, being able to reproduce the mathematics that were done by Warfield and others. Just on a personal note, I struggled with trying to figure out how to do and reproduce all the published mathematics that Warfield did in a couple of his books. And I was using computers to do that. And it didn't dawn on me that what was going on until we did a workshop with Warfield, and I asked him, I said, the largest matrices I could find, I think it was like 36 by 36. And I had written some code, and I tested it against some of his published matrices. And so I said, do you have anything larger than 36 by 36 that I can test my computer code on? He says, no. He said, I don't have anything larger than 36 by 36 because that's the largest I can do in my head. And so it told me right then that he was doing all this stuff by hand. And so he didn't really have to worry about computer data types, whether it was a Boolean or a binary or a digital, whatever kind of number it was. That was all, he didn't have to worry about that. And that was the tools that we had today with the computers were actually a barrier to that. And so we were able to, I think, effectively address that. Now we have another barrier, kind of a conceptual barrier, and I want to talk about that, and it's kind of the logical relation properties. When we talk about the Boolean matrices, the binary matrices, the directed graphs, basically directed graphs, and then the matrices that represent these, most people talk in the language of mathematicians, and they talk in the language of different orders on sets. And so they'll talk about logical relation properties in terms of how these logical relation properties impact different kinds of sets. And the first thing that I found that this is not a uniform approach. A few of these names for these different kinds of sets are uniform, but some of the ones that are really important to the structural modeling community have different interpretations. But each one of these different types of set descriptions are described in their logical relation properties. So it's very clear if you step past the idea of a totally ordered set, or a strict total ordered set, or a partially ordered set, or a completely ordered set, or a totally connected partially ordered set. All those things mean something in logical relationship terms to mathematicians, but they can all be described precisely in logical mathematical, logical relation properties. So Mary and I decided to actually create the number of permutations and give a small example of each one of the 27 classes of logical relationship properties that you would find that would structure a system. And so by stepping past these ideas, which are kind of uncertain in certain areas, so if you remember back, I said one of the things that we want to do is we want to eliminate uncertainty. We want to reduce complexity by eliminating uncertainty. So what we do is we eliminate the step of talking about logical relationships in terms of set ordering. And we eliminate the set ordering terms and we go right straight to the logical relation properties. And then we specifically talk about and we specifically address the logical relation properties that order the system. And that way it takes out the uncertainty of how that maps to a set. We don't care if it's partially ordered set. We don't care if it's antisymmetric. We don't care about that because we have stepped past that. We've eliminated that uncertainty of how to interpret that and have gone straight to the logical relation properties. As you can see here, of course, there's reflectivity, which applies only to one individual, symmetry, which applies to two individuals, and transitivity, which applies to three or more individuals. And what we found in our work is symmetry is the key organizing logical relationship that we have found that allows us to start classifying and dealing effectively with these types of problems. And so if we look at these three types of symmetry, we have these three types of symmetry essentially generate three types of structures, of system structures. And we're looking at asymmetric logical properties create a hierarchy. Symmetric logical properties create a network. Now, Forrester's systems thinking and systems dynamics, they're symmetric. You have feedback. You have in the mathematics and in asymmetric chains and in program planning especially, and you'll find that within the program planning that was done by Warfield early on, the whole idea was to create specific functional chains that had no feedback. And so when you're planning a process, feedback is your enemy. And I think also Kevin pointed this out. And then non-symmetric. Here we have systems that basically are a hierarchy of networks. And the non-symmetric type is mostly what you run into. And the key paper that Kevin pointed to of Warfield's, which was binary matrices, gives a very specific technique of how you can decompose and find these types and analyze these types of non-symmetric systems and break them into their component hierarchies and networks. Once you take a non-symmetric system and you break it apart, then you can use, on the hierarchical part, you can use your hierarchical analysis techniques. And on the network side, you can use your symmetric analysis techniques. And these are quite different. So it's really important, we believe, to be able to have mechanisms that allow us to, one, go in and find the structure in an unstructured problem space. Once we find the structure in an unstructured problem space, Then we need to be able to analyze that structure and break it into its component parts, asymmetric parts and its symmetric parts. Logic will play an important role in the asymmetric areas. So as I've said, we've essentially are making a series of small web applications that focus on fundamental components and very restricted, one component at a time, one concept. So in our current complexity reduction research, we're working on a problem we call the 19 cities problem. It's a simple example of ordering 19 cities. There's YouTube videos on how to do this. There's code on ResearchGate. If you have any questions or are interested and can't figure it out, be sure and let us know. And Kevin's working with the Future World Center, and as you pointed out, these people are working with extremely complex applications. And they use all these different techniques. But we're not to the level yet where we have enough fundamental components detailed to the point where we can interface those and actually address more complex applications. And that's our goal. Our goal is to essentially be able to come to a complex situation, get a quick analysis, then go to our menu pick list of our techniques, get those, put them together, and then analyze the situation. And that will give us a dynamic ability to create connections or aggregations or combinations of different approaches that are specifically tailored to the problem at hand. One of the things that I found is we have these static techniques, and so you take a static technique, and if that's your technique, you apply it to everything, and it's not very adaptable. So also, I think as Kevin alluded to, we're doing open source code, so we want to do code and evaluation components. So the abstract relation type piece is used to organize this information.
Joe, I think we lost them.
Yeah, I think we did too, but I'm going to just keep going with it. We'll record it and just put it up.
All right.
Yeah. And the abstract relation type is used to actually organize the information that's needed to address each specific component that we will use in the adaptable space. It has three parts. It has formal description, which is prose, and then we have a graphic representation with directed graphs, and then, of course, the mathematical equations and the computer code. Key differences between abstract relation type and the augmented model exchange isomorphism is the fact that the augmented model exchange isomorphism is the 27 different combinations of logical relations that we put together to identify specific structural ordering. So that allows us to step past the idea of partially ordered sets or totally ordered sets or whatever, and just not think about those, not use those because of the uncertainty associated with them, and to step over and just use the AMEI logical relation groups. And those are used to guide our investigation. Here's an example. Well, this is not, yeah, so this is an example of augmented model exchange isomorphism, which has the prose component, which lists what the logical properties are, gives a structured graph representation of those properties, and a matrix representation of the graph and those properties. And these are isomorphic. So any one of these specific representations will be the same. So you can take a system, you can, if you only have a matrix representation of it, you can generate a graph and a prose. And of course, you need to have the context here that talks about important components that impact the application of this technique. So I talked about the logical data types, and I also talked about the difficulty of implementing some of these mechanisms that were developed by people who either did their mathematics by hand or developed their own compilers or types of analog or digital computers to do the work. And this is an example. So Warfield augmented Boolean operations by adding ordering. He had added the concept of order to Boolean operations. And the technique that we use today to implement these Boolean operations and binary matrices, but use decimal operations, the technique that we use is based on the analysis of these two columns. These two columns are the same, except for 1 plus 1 equals 2 in decimal operations, and 1 plus 1 equals 1 in Boolean operations. But because Warfield added order to Boolean operations, and decimal operations already have the idea of order, we just do all of our calculations and our matrix calculations with decimal operations, and then we run them through, map them through a filter that translates the answer back to Boolean operations. What that filter does basically is says, if it's a 0 in decimal, it's a 0 in Boolean. And if it's greater than 0 in decimal, then you map it to a 1 in Boolean. And this has been a technique that has allowed us to use modern compilers and modern computing systems to implement these types of logical systems. So the logical data type semantics, and as we've talked about so far, is we have an unknown situation, we're going to structure it. So we really have to have empirical data, and we also have to have the technique to use logical properties and logical inference based on the empirical data. So what we've done is we've used the ubiquitous availability of colored computers and computing devices everywhere to add semantics to the Boolean logic. So in this particular case, we have a 0 with a red background, which means known false. It says 0 is false, and red background means, yes, we know from empirical data that that's false. And then a 1 with a green background means known true. Means, yes, from empirical data, we know that this is true. And then a 0 with a yellow background, in this particular case, means it's unknown. Means we really have no information, no empirical information or no inference information about this element. And then a blue one, a 1 with a blue background, is inferred true. So yes, we say, okay, we believe that this particular element is true, and we do this, and we know this because of the inference that we applied to the structure. Called a Simpson augmented Boolean algebra, and it's used to reduce the cost of collecting empirical data in any given situation that has been structured, that the analysis of the situation has been structured this way. And of course, over time, the semantics for 0 and 1 have changed. Boole, in his original book, The Investigation of the Laws of Thought, 0 meant nothing and 1 meant the universe. Now we'll just kind of go over a little bit of the 19 cities problem, and which uses the structuring relationship north of, and show that this is a strictly ordered system structure, what that means in logical property terms, and also its objective is to minimize the cost of the structuring, and will provide also some automated functional test ideas and how we actually did this. So the 19 cities problem is fairly straightforward. We have 19 cities, we know they exist. We know we have a global structuring relationship north of that we want to structure these systems. But we really don't know how each individual city is related to the others. So we're going to use empirical data. We're going to go out and find out. We're going to ask. We're going to inquire. We're going to inquire about the relationship of these cities. And we're going to reduce and minimize the cost of the inquiry by using inference. So for north of, it's asymmetric, irreflexive, and transitive type of logical properties. For the ISM in this area, basically this is where we collect the empirical data. Someone in the data space, in the problem space, is going to have to find that information and provide it to us. And then of course in the SIM area, what the technique is to use our analytical processes to minimize the data collection costs and to order the systems. So when we did the software, it's one of the challenges we had was how do we test it? What's the functional test? And if you think about what our goal is, and what we said is we walk into a situation where we have an unknown structure, unknown problem structure. So then we create a structure of the problem. Well, you can't test that because when you first walk into it, it's unknown. So you really don't know if you have the right structure or not. So we tested the method by creating a known system structure. Then we randomized that and created an unknown system structure. Then we initialized the methods and did our methods of system discovery. We applied the steps until it was done. Then we compared what the system we discovered back to the known system structure. And so this is the way the matrix looks like when you start the problem. Essentially, we have zeros on the diagonal. Red means known faults. The way this is read is just say, okay, city 1 is north of city 1. There's a red 0. That's known faults. We know that cities are not north of themselves. So every city is not north of itself. That's what the red 0 means. Yellow background means unknown. As we stated, the initial conditions, we really don't know how these cities are related to each other. We have to get empirical information to get that, to find that out. So we apply our techniques, we go through, and this is our final system structure that comes out at the end. Again, as I said, the information, the steps, the mathematics, everything, how to do this is all available on the web. So what we have here, again, is we have the red background, so we know these are false. We have quite a few red ones. The green ones, known true. We have the green ones, and we had to, there would cost some resources to get the green ones and the red ones. So the blue means inferred true. We have a lot of blue ones, and these were all inferred true at no cost, just by our analytical technique. And of course, the yellow background still means unknown. Now, you can see that there's some ambiguity in this final decision, but this was run as a system test by a computer simulation, and the computer knew that this was the final right answer. If this had been really an unknown situation, these last couple of iterations would have been done, and you would have had a slightly different outcome.
Joe, could you clarify, is that the reachability matrix?
Well, the in a reachability matrix is, I think, can be mapped to this, but I'm not quite sure it's the same thing. It's because we don't have ones on the diagonals. I think the reachability matrix has to have ones on the diagonals, but it's similar. It's kind of a similar idea, and it's. But we can talk about that, and I can actually work up the specific answer to that for the next Saturday meeting, and but it is. if you're looking at Warfield's work, you remember that the reachability matrix has to have the identity matrix in it, right? So this is kind of the structured matrix plus the identity matrix, I think, equals the reachability matrix. But I'll check that. And then this is the empirical data that comes out. Well, the main thing to look at here is that the empirical data increase is just normally about the same, but the inferred data starts out with low numbers, but it gets really high fast. So as you get larger matrices and more information, you get a lot more inferential power, inferred data power. And I think this is one thing Kevin really talked about, is this is very scalable. It's a scalable approach, and the larger the matrices, really the more power it has. This is, again, a graph of the data we just looked at. And one of the areas of research actually is to determine this cross. You can see the blue is empirical data. It's kind of about the same, kind of linear. You see the inferred data content, it's kind of low, and then it starts going up pretty fast. So two areas to look at is what algorithms, what approaches can increase the number and how fast this increases. Instead of this way, we want it to go up almost fast as it can. And number two, we want to move this crossover point closer to the origin. So there's a lot of interesting questions in this that will actually be determined by the methods that you use, and a lot of research opportunities in that area. So, given that, are there any questions besides, is that a reachability matrix, which I will answer later on? Okay. Well, hearing none, I think what I will do is stop this broadcast and thank everyone for their participation. Thank you, Kevin.
Thanks, Joe. Are we going to the third hangout now?
We'll do that in about 11 minutes.
All right.
Go to the third one, and I'll invite everybody.
Okay, bye.